for the AET-GEM Environment Agency partnership was to produce a disposable, low-skill, low-cost, sensitive, one-shot disposable biosensor for the quantitative measurement of ammonia in sewage effluent. With the successful launch of the HandyLab, we anticipate considerable interest from the UK water companies. We anticipate the sale of up to 800,000 sensors per annum in the UK if these two specific sectors take up the task.
This involves our measuring water quality regularly. This is Ross, one of our samplers. Ross is making pH and dissolved oxygen measurements on site, and he's filling up bottles to take back to the laboratory for other analyses. Ammonia is the most widespread toxic pollutant in our rivers. It's a breakdown product of human and animal waste. It can enter rivers in a number of ways, from badly operated sewage works, from farm slurry spillage, or from industrial discharges. We set limits on the amount of ammonia that can be tolerated by the river's ecosystem, and we sample regularly to make sure they're not exceeded.
Current field testing for ammonia instrumentation falls into two discrete categories: ion selective electrodes and colorimetric test kits. Ion selective electrode technology is too insensitive. Colorimetric tests are based on the same biochemistry as the large instruments set up for carrying out laboratory tests. However, for a handheld field instrument, these tests are slow, dependent on ambient temperature, and inaccurate, i.e. they do not deliver the required error and bias required for such a test. They also require some degree of skilled sampling preparation prior to the actual measurement of the sample by the instrumentation. Both tests are also prone to interference from metal ions. This is especially problematical for the ion selective electrode, and both require frequent calibration by the end user. Our technology, on the other hand, is a completely portable battery-operated system which requires only minimal operator skill for sampling, i.e. a dip test and test operation. Our system compensates for varying water sample temperature. The result is delivered as a digital output in parts per million of ammonia within 5 minutes. Following the test run, the biosensor is collected for recycling. The base sensor is a screen-printed carbon electrode impregnated with an electrocatalyst Maldona's blue. These materials are prepared and screen-printed by GEM. The electrodes are subsequently coated with a combination of buffers, enzymes and other components which make the biological part of the biosensor. This task is carried out by AET. The electrode is polarized at 50 millivolts, and at this potential the cofactor NADH is converted to NAD with the loss of electrons. These electrons are detected by Maldona's blue with a change in the current at the electrode surface. In the presence of ammonium ions, the enzyme on the electrode surface oxidizes NADH to NAD independently of the electrode potential. This results in a lower current at the electrode surface. The higher the ammonia concentration in the sample, the lower the current at the electrode surface. The end user only sees a digital output in parts per million of ammonia in the sample analysed. Actual lab testing of the HandyLab plus biosensors. Currently, a Palm PC controls part of the software on the system. The running software is activated and waits for the instrument to come up to operating temperature, which takes approximately 20 seconds. Meanwhile, the water sample is collected accurately by dipping the sensor into the water sample to be tested. The software then informs the operator to insert the biosensor and continue the test. The biosensor is then inserted into the HandyLab, the sample then incubated for a pre-designated time prior to measurement. Currently, the measurement is plotted as a curve on the Pocket PC. This will be made redundant in the next iteration, and all controlling and analysing software will be integrated into the HandyLab. Following a total test time of just over 5 minutes, the concentration of ammonia is output in parts per million. This data can be recorded physically, but will also be saved by the onboard software. The software will enable the storage of 50 measurements, which will be downloadable at the end of the day. The biosensor manufacturing follows 8 distinct processes: ink preparation, screen printing, well preparation, enzyme formulation, biodeposition, drying, cutting and packaging. Ink preparation includes the formulation of the right ratios of resin, solvents, mediators and other active ink components, either carbon for the working electrode or silver for the reference electrode. These inks are subsequently mixed and roll milled. This delivers the efficient dispersion of the components followed by the consistent milling of the sample. This ensures that the particle sizes of the inks fall within the required specification for screen printing. This is tested by the fog measurement or fineness of grind. Once the particle size has been passed by the QC test, then the rheology or overall flow characteristics of the ink are tested. The ink is now ready for screen printing. The screens, which have already been designed to incorporate the shape and distinctive components of the biosensors, are flooded with one of the inks. The 2 different inks for the composition of the biosensor are printed separately, with the inclusion of a curing step between each print. As you can see, a squeegee comes across the screen, forcing the ink through the screen pattern. The printed card is then cured, ready for the next print layer. Once both layers have been cured, they are visually QC'd and then random electrodes from each printed sheet are electrochemically tested. Following QC approval, the electrodes are ready for well construction and enzyme deposition. We pre-construct our sampling system in strips ready for adhesion to the complete printed card. The enzyme components are then formulated and the activity of the enzyme cocktail checked prior to deposition. We then use our dispensing biorobot to deliver the required volumes of enzyme to the sensor surface. This equipment allows us to generate large numbers of completed biosensors in a very short time. The complete cards are then subjected to a drying step. This produces freeze-dried electrodes, currently in batches of 1,500 sensors per batch. The enzyme formulation contains patented stabilizer components which ensure the retention of enzyme activity during the drying process and the onward storage of the electrodes. The storage requirement for this biosensor are at least 6 months at room temperature. With our stabilization technology and expertise, we have easily met this shelf life requirement. Once the electrodes have been successfully dried, we cut out the individual sensors via a hydraulic cutter and package the sensors using humectant plastic resealable pots. The electrodes are then tested to ensure the QC requirements are met. Then each batch of electrodes are pre-calibrated prior to dispatch to the customer, and it will be relatively straightforward to develop nitrate and phosphate sensors using the same platform. In the longer term, we can look at sensors using antibody technology to address the apparently unattainable challenge that the Water Framework Directive is raising.